Chapter 10 continued, The Shapes of Molecules. Section 10.1, Depicting Molecules and Ions with Lewis Structures. Using figure 10.1, which is shown on this slide, we will discuss the steps for writing Lewis structures for molecules that have only single bonds. We will outline the steps in this slide, and we will use the steps for writing Lewis structures for nitrogen trifluoride very soon. Step 1 is to convert the name of the compound to its molecular formula and then put the atom of lower electronegativity value in the center. Surround the central atom with the remaining atoms, keeping symmetry in mind. Step 2 is to determine the total number of valence electrons available from the atom in the molecular formula. Remember, group A numbers from the periodic table indicates how many valence electrons each atom owns. In step 3, we connect the central atom to each of the surrounding atoms using a single bond. Remember, each single bond accounts for 2 electrons. In step 4, we distribute any remaining electrons around each surrounding atom so that each atom ends up with a total of 8 electrons. Electrons are placed around the surrounding atoms first because they are usually more electronegative. Place electrons in pairs around the atoms. Remember, hydrogen has a duet and can only have a maximum of 2 electrons. If there are any remaining electrons, they go on the central atom. Check to see if all atoms are surrounded by 8 electrons and that all available electrons were used in the Lewis structure. Now let's do our example with nitrogen trifluoride. The molecular formula for nitrogen trifluoride is NF3. Generally speaking, the least electronegative atom is usually given first in the formula of molecular compounds. The exception to this, of course, is with hydrogen. Step 1. Place nitrogen in the center and surround the nitrogen with the 3 fluorine atoms. Try to place the fluorine atoms around the nitrogen as symmetrically as possible. The reason for this step will become clearer later in this chapter. Step 2. Determine the total number of valence electrons that are available. Nitrogen is in group 5A and thus has 5 valence electrons. Fluorine is in group 7A and will have 7 valence electrons. Since we have 3 fluorine atoms, the total valence electrons supplied by the 3 fluorine atoms are 21 electrons. Therefore, we have a total of 26 valence electrons at our disposal. Step 3. Connect the central nitrogen atom to the 3 surrounding fluorine atoms with a single bond. Each single bond uses 2 electrons for a total of 6 electrons used. Notice we still have 20 electrons that are available to us. Step 4 is to distribute the remaining electrons in pairs so that each atom that is surrounding the nitrogen ends up with a total of 8 electrons. Therefore, we are to place the lone pair of electrons around the surrounding atoms first, and if we have any left over, they go on the central atom. So we need to give each fluorine 3 lone pairs of electrons. Remember, symmetry is important for the placement of lone pair of electrons as well. Since each fluorine atom requires 3 pairs of electrons, or 6 total electrons, notice we have used 3 times 6 or 18 electrons, making sure each fluorine atom is surrounded by 8 valence electrons. This means we have 2 electrons or 1 electron pair left over, which now go on the central nitrogen atom. All we have to do now is to be sure every atom in the compound is surrounded by 8 electrons and that we have used up all of the available valence electrons. Each atom is surrounded by 8 electrons, and since we have used up all the available electrons, this is a completed Lewis structure for nitrogen trifluoride. Using these 4 steps, you can write Lewis structures for any singly bonded molecule whose central atom is carbon, nitrogen, or oxygen. Remember this, however. Hydrogen atoms form 1 bond, carbon atoms form 4 bonds, nitrogen atoms form 3 bonds, and oxygen atoms form 2 bonds. The halogens form 1 bond when it is a surrounding atom, but they have the ability to form more than 1 bond when they are the central atom. Fluorine will always be a surrounding atom. Let's work through a sample problem. In sample problem 10.1, we are asked to write the Lewis structures for Freon, which has the chemical formula CCl2F2, which is one of the compounds responsible for the depletion of the ozone layer. Freon was used as a refrigerant. Secondly, we are asked to write the Lewis structure for PCl2-. Let's start with Freon. Since carbon is listed first in the molecular formula, it is the least electronegative atom and is the central atom. Surround the central atom with the surrounding atoms, and it is completely arbitrary where the surrounding atoms are placed, meaning where do you put the chlorines versus the fluorines. However, we need to keep in mind of symmetry. So we will alternate the surrounding halogen atoms around the central carbon atom, and we will do this as symmetrically as possible. Now determine how many valence electrons we have at our disposal. Hopefully you determined that you have 32 valence electrons. Now connect each one of the surrounding atoms to the central atom with a single bond. Since we have used 4 single bonds, we used 8 valence electrons, so we have 24 valence electrons left over. Now give each of the surrounding atoms a full octet of electrons by placing electron pairs around the atom until each atom is surrounded by 8 valence electrons. Once you have done this, you are done. We have used up all the valence electrons, and each atom is surrounded by 8 valence electrons. So we are completely done. Now I would like for you to work through part B on your own, but I will give you a little hint. Whenever you have an ion, and the ion is negatively charged, you add 1 electron for each negatively charged that is placed on the ion. For any ions that are positively charged, they lose electrons. Okay, so here is the solution. Hopefully your answer is very similar to the one that's shown here. I'd like to talk to you about a couple of things. So notice in step 2, when we're determining the number of valence electrons, phosphorus has 5 electrons, each chlorine has 7 electrons, and we added 1 electron for the negative charge for a total of 20 valence electrons. We then formed our Lewis structure, but now we have to account for the fact that this is an ion that is negatively charged. So we draw square brackets around the entire Lewis structure, and we add the charge in the upper right-hand corner. So that's what we would have to do for all ions, whether they are cations or anions, is to put the Lewis structure in brackets and put the charge in the upper right-hand corner. So hopefully you got the same answer that is shown here. If not, let me know and we will work through it together. And sample problem 10.2 wants us to write the Lewis structure for a more complex compound, one that has 2 central atoms and other atoms that are around it. The compound in this sample problem is methanol, which is used as an alternative fuel source in some automobiles. The chemical formula for methanol is CH4O. Since hydrogen atoms can only form 1 bond, the carbon atom and the oxygen atom must be the central atoms. Place the atoms beside one another. Remember, carbon atoms like to form 4 bonds, while oxygen atoms like to form 2 bonds. If the carbon atom is connected to the oxygen atom, then carbon needs to be bonded to 3 hydrogen atoms, and the oxygen needs to be bonded to 1 hydrogen atom. Place the hydrogen atoms around the carbon and oxygen so that the carbon will be connected to 3 hydrogens and oxygen is connected to only 1. Determine how many valence electrons we have available to us. Hopefully you found that we have 14 valence electrons. Now connect all the atoms together with a single bond. When you do this, notice you have used 10 of the 14 available valence electrons. Also notice each hydrogen atom has 2 electrons and the carbon atom has 8 electrons, but the oxygen atom only has 4 electrons. Therefore, the remaining 4 valence electrons go on the oxygen atom. Please be sure to work through the follow-up problem and let me know if you have any questions or concerns. So what did we do if we've used up all of the available valence electrons and the central atom is not surrounded by a total of 8 valence electrons? Sometimes we will find this to be the case. All of the surrounding atoms are happy because they are surrounded by 8 electrons, but our central atom is electron deficient. If there are not enough electrons to give the central atom a full octet of electrons, or 8 electrons, we need to form a multiple bond. This is step 5, and it states if the central atom does not have a full octet, change a lone pair of electrons on a surrounding atom into another bonding pair to the central atom, thus forming a multiple bond. Keep in mind, we only form multiple bonds when the central atom is electron deficient. So let's do an example where we need to use multiple bonds in order to give the central atom a full octet of electrons. In this sample problem, we are asked to write Lewis structures for ethylene, which has the chemical formula C2H4, and nitrogen gas, which is N2. What is our plan? We need to follow steps 1 through 4 in order to see if the central atom has a full octet or not. If it does, we are all set. If it does not, we need to use step 5. Let's start with ethylene. To write the Lewis structure for ethylene, we are going to follow the 4 basic steps for writing Lewis structures. Ethylene is another example of a compound that has 2 central atoms, the carbon atoms. Place the 2 carbon atoms beside each other and surround the carbon atoms with 2 hydrogens each. Determine how many valence electrons we have, which should be 12. Connect the atoms together with single bonds. Notice each hydrogen atom is happy because they are surrounded by 12 electrons, which is all they can have. Also notice that by connecting the atoms together, we have used 10 of the 12 electrons we had available to us. Now put the remaining lone pair of electrons in one of the carbon atoms. It does not matter which one. The carbon atom that has the lone pair of electrons is happy because it is surrounded by a full octet of electrons, but the other carbon atom is not happy as it is only surrounded by 6 valence electrons. Since we do not have any valence electrons left over, we need to try multiple bonds. Move the lone pair of electrons off of the carbon atom and make another bond between the carbon atoms, producing a double bond. Now this is a good Lewis structure of ethylene because all of the atoms are surrounded by an octet or a duet of electrons. Please write the Lewis structure for nitrogen on your own before moving on to the next slide where you can check your work. Here is the solution for part B. Were you able to determine the nitrogen atoms in N2 are connected with a triple bond? If yes, great job. If no, do you understand now how to work through this problem after you have seen the solution? If not, please let me know. Please work through the follow-up problem before moving on to the next slide, and let me know if you are having any difficulties writing Lewis structures. Sometimes we will encounter molecules and ions where the arrangements of atoms are not adequately described by a single Lewis structure. This usually occurs when the multiple or ion contains a double bond next to a single bond. Consider the molecule ozone, which is O3, which is a bent molecule with 2 equal oxygen-oxygen bond lengths. Because each oxygen atom contributes 6 valence electrons, the ozone molecule has 18 valence electrons at its disposal. When we write the Lewis structure for ozone, we find that we must have 1 oxygen-oxygen single bond and 1 oxygen-oxygen double bond in order to attain a full octet of electrons around each oxygen atom as shown on this slide. However, this structure cannot by itself be correct because it requires that 1 oxygen-oxygen bond be different than the other, which does not agree with the observed structure for ozone. Double bonds are usually shorter than single bonds, but both of the bonds in ozone are of equal length. Keep in mind that the placement of the double bond could appear on either the right side or the left side of the molecule. The placement of the atoms in these 2 alternative Lewis structures for ozone is the same, but the placement of electrons is different. Lewis structures of this sort are called resonance structures. A resonance structure is defined as one of or 2 or more Lewis structures for a molecule that cannot be adequately depicted by a single structure. Resonance structures differ only in the placement or position of the bonding and lone pair of electrons. The resonance structures are separated by a resonant arrow, which is a double-headed arrow. One resonance structure can be converted to the other resonance structure simply by moving lone pairs of electrons to bonding positions and vice versa. A species like ozone, which can be depicted by more than 1 valent Lewis structure, is called a resonance hybrid. Resonance structures or forms are not real bonding depictions. They represent hypothetical structures. Ozone does not change back and forth between its two resonance forms or structures. The real structure of a resonance hybrid is an average of its contributing resonance forms. To understand why certain molecules retain more than one resonance structure, we can draw one of two analogies, the mixing of paint and the mule. Let's start with the mixing of paint. Red and blue are both primary colors of paint pigments. An equal blend of red and blue pigments produces purple pigment. Purple paint does not oscillate between its two primary colors. It is not red part of the time and blue the rest of the time. The same is true for the mule. A mule is a genetic mix or a hybrid of a horse and a donkey. It is not a donkey one minute and a horse the next. Similarly, molecules such as ozone cannot be described by a single Lewis structure in which the electrons are locked into a particular arrangement. Therefore, the ozone molecule is a blend or hybrid of two resonance structures. We cannot describe the ozone molecule in terms of a single Lewis structure. Lewis structures depict electrons as localized either on an individual atom as lone pairs or in a bond between two atoms, shared pairs. In a resonance hybrid, electrons are delocalized. Their density is spread over a few adjacent atoms. An example of this is the resonance hybrid of the ozone molecule. Resonance hybrids often have fractional bond orders due to the partial bonding. To determine the fractional bond order, you sum up the total number of bonded electron pairs divided by the sum of the bonded atom pairs. Therefore, the fractional bond for ozone is 1.5. Do you see this? In this sample problem, we are asked to write resonance structures for the nitrate ion. This is our second encounter with an ion, and we need to remember what to do about the electronic charge. Remember, one electron is added to the total number of valence electrons for each negative charge associated with an anion, and one electron is subtracted from the total number of valence electrons for each positive charge associated with a cation. Nitrogen is the central atom, and it is surrounded by 3 oxygen atoms in a symmetrical fashion. When determining how many valence electrons we have to work with, we need to remember to add 1 electron for the negative charge on the nitrate ion. Therefore, we have a total of 24 valence electrons. Upon completions of steps 3 and 4, you should have the nitrogen atom connected to 3 oxygen atoms with a single bond, and all of the oxygen atoms should be surrounded by an octet of electrons. The entire Lewis structure needs to be placed in brackets with the 1- charge in the upper right-hand corner. Since nitrogen only has 6 valence electrons, we need to move one of the lone pair of electrons from one of the oxygen atoms to a bonding pair of electrons to form a double bond. Since all of the oxygen atoms are equivalent, we can write 3 different resonance structures, making a double bond between each of the oxygen atoms and the nitrogen atom as shown on this slide. Notice each of the resonance structures are in brackets with the charges in the upper right-hand corner and are separated by resonance arrows. Notice that the arrangement of atoms is the same in each structure, only the placement of electrons differ. In writing resonance structures, the same atoms must be bonded to each other in all structures, so that the only difference are the arrangement of electrons. All 3 Lewis structures taken together adequately describe the nitrate ion, in which all 3 nitrogen-oxygen bond lengths are the same. Please be sure to work through the follow-up problem before moving on to the next slide. Do not hesitate to contact me if you have any questions or concerns. The concept of resonance is very important in describing the bonding that takes place in organic molecules, especially organic molecules that fall into a class called aromatic compounds. One such aromatic compound is benzene. Benzene has the molecular formula C6H6, where all 6 of the carbon atoms are bonded in a hexagonal ring, and there is only 1 hydrogen atom bonded to each carbon atom. Benzene has 2 important resonance structures in which alternating single and double bonds have different positions. The actual molecule has 6 identical carbon-carbon bonds because there are 6 carbon-carbon bonds and 3 electron pairs delocalized over the 6 carbon atoms, often shown as a dashed circle or simply as a circle. Notice in this slide the colors are once again used to represent the individual resonance structures and the hybrid structures. When we write Lewis structures, we are actually describing how the electrons are distributed in a molecule or ion. In some cases, we can write several different Lewis structures, all which obey the octet rule. So how do we decide which resonance structure is the most reasonable or the most important to the overall hybrid? One way to determine which resonance structure is the most reasonable or the most important is to do some bookkeeping of the valence electrons to determine the formal charge of each atom in the Lewis structure. Formal charge is the hypothetical charge on an atom in a molecule or ion that is equal to the number of valence electrons minus the sum of all the unshared and half the shared valence electrons. To calculate the formal charge of an atom, we assume the bonding electrons are shared equally. Let's calculate the formal charges for all the oxygen atoms in ozone using the equation that's shown on the top of this slide. The resonance structure for ozone on the left is Roman numeral 1, and the one on the right is Roman numeral 2. So that we are not confused and to ensure we are calculating the formal charge of the same oxygen atom, let's assign letters to each of the oxygen atoms. The oxygen atom on the left that is doubly bonded to the central atom is A, the central atom is B, and the singly bottom atom is C. This is for Lewis structure 1. Let's calculate the formal charges for each atom in structure 1, starting with oxygen atom A. Oxygen A has 6 valence electrons. It has 4 unshared electrons and 1/2 of 4 bonded or 2 electrons. Therefore, the formal charge on oxygen A is equal to 6 minus 4 minus 2, which equals 0. Do you see this? Try calculating the rest of the formal charges for all of the oxygen atoms remaining before moving on to the next slide where you can check your work. So here are the solutions for the remaining 5 oxygen atoms. How did you do? Notice that the formal charges for the atoms in the molecule must equal the overall charge on the molecule. Ozone is a neutral molecule, so the sum of the formal charges must equal 0. The sum of the formal charges of an ion must equal the ionic charge. As a general rule, when several Lewis structures are possible, we will use the following criteria to help us choose the most important resonance structure. Smaller positive or negative formal charges are preferred to larger formal charges. Like formal charges on adjacent atoms are not desired. Negative charges should reside on the more electronegative atom. The most stable Lewis structure will be the one that has the smallest formal charges. To apply these criteria, let's compare the formal charges to the 3 resonance structures for the cyanate ion, NCO-. Resonance structure 1 is eliminated right away because it has larger formal charges than the other 2 resonance structures. Notice in structures 2 and 3, the negative formal charge is located on the nitrogen atom in structure 2 and is located on the oxygen atom in structure 3. Since oxygen is more electronegative than nitrogen, it gets the negative charge. While both resonance structures 2 and 3 are significant contributors to the overall hybrid for the cyanate ion, structure 3 is the most important resonance structure. Do you have any questions? Do not confuse formal charges with oxidation numbers. For formal charges, the atoms share bonding electrons equally, so each atom has half of them. For an oxidation number, the bonding electrons are transferred completely to the more electronegative atom. The octet rule is simple and useful in introducing us to basic concepts of bonding, and because of this, we may wrongly assume that it's always obeyed. This is not the case in many situations involving covalent bonding. These exceptions to the octet rule are of 3 main types. Molecules and polyatomic ions in which the central atom has fewer than an octet of valence electrons. Molecules and polyatomic ions containing an odd number of valence electrons. Examples of these can be seen on this slide. The first type of exception occurs when an atom in a molecule or polyatomic ion is surrounded by less than an octet of electrons. While this exception is relatively rare, We see it quite often with compounds of boron and beryllium. To illustrate this, let's consider boron trifluoride, BF3, which can be seen on this slide. There are only 6 valence electrons around the central boron atom, while each fluorine atom is surrounded by 8 valence electrons. Calculate the formal charges for each atom in boron trifluoride. What did you come up with? The formal charge on each atom in boron trifluoride is 0. Now, what if you were to complete the octet around boron by forming a double bond? You should try this on your own, and what you will find out is that you can write 3 equivalent resonance structures. If you were to calculate the formal charges for each atom in each one of the resonance structures, you would determine that the fluorine that is engaged in the double bond will have a formal charge of +1, and the boron would have a -1 formal charge. This is not a good situation for boron trifluoride, where the most electronegative atom, which is fluorine, has a +1 charge, while the least electronegative atom, boron, has a -1 charge. Therefore, in the Lewis structure in which there is a boron-fluorine double bond, are less important than the one in which there are fewer than an octet of valence electrons around boron. Since fluorine is the most electronegative atom, it will never form more than one bond. Fluorine will always have a single bond. Now let's look at the second time of an exception, where we have molecules or polyatomic ions that contain an odd number of electrons. The majority of molecules in polyatomic ions, the total number of valence electrons is even, and complete pairing of electrons is possible. In a few molecules in polyatomic ions, such as those that have nitrogen, chlorine, or oxygen as the central atom, the number of valence electrons may be odd. Complete pairing of these electrons is impossible, and an octet around each atom cannot be achieved. Let's look at nitric oxide, which has the chemical formula NO2. The 2 most important Lewis structures for nitric oxide can be seen on this slide. Which Lewis structure is the most correct? Notice the Lewis structure on the left has the lone electron on the nitrogen atom, while the Lewis structure on the right has the lone electron on the oxygen atom. To determine which is the most correct, calculate formal charges. Both the nitrogen atom and the oxygen atom in the Lewis structure on the left will have formal charges of 0. However, this is not the case for the Lewis structure on the right. The nitrogen atom will have a -1 formal charge, while the oxygen atom will have a +1 formal charge. Since oxygen is more electronegative than nitrogen, it should contain both pairs of electrons, and the lone pair of electron will be on the least electronegative nitrogen atom. The lone electron in molecules or polyatomic ions will always be on the least electronegative atom. A molecule with an odd number of electrons is called a free radical. The largest class of exceptions to the octet rule is expanded valence shell. This exception includes molecules and polyatomic ions in which an atom, which is usually the central atom, has more than an octet of valence electrons. When we draw a Lewis structure for phosphorus pentachloride, PCl5, we need to expand the valence shell and place 10 electrons around the central phosphorus atom. Other molecules and ions with expanded valence shell include sulfur, chlorine, iodine, arsenic as the central atom. Basically, any element in row 3 or higher on the periodic table can have an expanded octet. We will never see an expanded octet for any element in period 2, and here is why this is the case. Remember, elements of period 2 have only the 2s and the 2p valence orbitals available for bonding. Since these orbitals can hold a maximum of 8 electrons, we never find more than an octet of electrons around period 2 elements. Elements in period 3 and beyond have the sp and the d orbitals that can be used in bonding. The presence of the d orbitals allow period 3 elements and beyond to have an expanded octet. Size also plays an important role in determining whether or not an atom in a molecule or polyatomic ion contain an expanded octet in its valence shell. The larger the central atom, the larger the number of atoms that can surround it. The size of the surrounding atoms is also important. Expanded octets occur most often when the central atom is bonded to smaller and more electronegative atoms such as fluorine, chlorine, and oxygen. Let's work through a problem that deals with writing Lewis structures for molecules or ions that are exceptions to the octet rule. Here we are asked to write Lewis structures for SClF5, phosphoric acid, and BFCl2, and then we are to pick the most likely Lewis structure for phosphoric acid. Since the Lewis structure for SClF5 is shown on the bottom of this slide, let's work through the solution for phosphoric acid before you move on to the next slide. Since phosphoric acid is the least electronegative atom, hydrogen atom does not count. It is the central atom. Determine how many valence electrons we have to play with, which hopefully will be 32. Connect each oxygen atom to the central phosphorus atom with a single bond, and then connect the 3 hydrogen atoms to an oxygen atom. It does not matter which 3 oxygen atoms you use. Give each oxygen atom an octet of electrons. We should have used up all the electrons, right? Notice we can write a resonance structure where we move one of the electron pairs located on the singly bonded oxygen atom to form a double bond between the phosphorus and the oxygen. Which is the most likely structure? To determine this, calculate formal charges for all the atoms in both structures. The structure with the lower formal charge will be the most likely structure. Hopefully what you should find is that the structure that contains the phosphorus-oxygen double bond is most likely. Why is this? To answer this question, please move on to the next slide. Sometimes we may see Lewis structures written with the central atom having an expanded octet, even though a Lewis structure can be written where all of the atoms have an octet of valence electrons. In our example, the Lewis structure for phosphoric acid without the phosphorus-oxygen double bond shows a formal charge of +1 on phosphorus and -1 on the oxygen. Both of these charges are removed when we give phosphorus an expanded octet in the second Lewis structure. It is important to realize here that formal charge is a useful but not a perfect tool for assessing the importance of contributions to a resonant hybrid. Recent theoretical calculations based on quantum mechanics suggest the Lewis structure in which phosphorus has an expanded octet and smaller formal charge is the best single Lewis structure for phosphoric acid. Please work through the Lewis structure for BFCl2 on your own before moving on to the next slide. Hopefully what you will find is that the Lewis structure for BFCl2 is very similar to the Lewis structure for boron trifluoride. If you have any questions or concerns, let me know.